Okay, so let me try this. Let me take wrong class. So I need to take attendance here. As I'm doing this, one thing which you should be able to see is the extra credit for the first exam that I said was going to be posted, finally got. What? No, this is fine. So the exam finally got, there we go, lecture notes are up. Okay. Okay, everything's happening all at once. Okay, cool, so the lecture notes are up now. What's also available on Canvas is the extra credit assignment that goes with the first exam. So that's posted, it's in the exam section. It's worth, what did I say, 10 points for you guys, and it's due on Monday. So you have some time to work on it. If you have any questions about it, I'm more than happy to talk about it with you during an office hour. And the way that I do my extra credits for assignments is a little idiosyncratic. So there's this cutoff at 90 points where if you got below a 90, you cannot get above a 90 points. So if you got, even though there's 10 points on there, if you got 85 points in your exam, you could only get 5 more points to bring yourself up to a 90. Also, if you were already above a 90, that means you can't get any extra credit any for the exam. And the reason why I have it set up like that is, well, first, if your exam is lower, kind of fairly low, it doesn't affect you at all. You can get all the available points. But it means for the A range, if you didn't get a 90 or above, so if you didn't get an A, you can only get up to a 90, just the very bottom of the A range. So that kind of says if you want to do especially well, you really need to do that the first attempt. What it also means is that if you're wanting the highest grade in the class, so if you're shooting for an A, you're really going to have to do pretty well in all the exams, and it means that you can't run up the score. So you can't just blow one exam completely out of the water by doing well and then adding on the extra credit. And if you do so well in one exam, you can maybe slack off for another one. So not allowing the people that already have a high score to get extra credit really says if you want the highest possible grade, you're going to have to keep doing well in every exam. So that's the reason for this sort of odd extra credit situation, but it's the way that I like to do it. Okay, so the extra, the extra credit I touched on. The lecture notes are posted, so let's get going. So I'm going to be working off the lecture notes that are posted, but I'm going to be writing it out on here, so it's a little more kind of closer to what class is like. Okay. So where we've been talking about is the chain rule, and the basic version of the chain rule, meaning not the rate of change one we touched on a little bit, but the one that's gotten most of our attention, says if we want to take the derivative of a composition of functions, then there are two parts to this. First is take the derivative of the outside function and then leave the inside function alone. Then there's a second part that says go back to that inside function, find its derivative, and that's multiplied out on the end of everything. So we've been using this a bunch. One case which looks sort of weird is, what if we want to find the derivative of e to the g of x? So one thing which looks weird here is that the inside function isn't really inside, or it doesn't look quite as inside a square root or inside a trig function, but the g of x is the inside function since it's up in the exponent. And if we want to use the chain rule on this situation, well, the first part says take the derivative of the outer function, the e to the x, but e to the x is its own derivative. So the first part of the chain rule, which has us differentiate this e, doesn't do anything. It's still e to the x. And then the inside function, which in our case is up in the exponent, stays there. So the first part of the chain rule, when your function is e raised to something other than x, is just right, you get the same function again. But then there is a second part of the chain rule, and what the derivative does in this case is you get that same function again, but then you multiply by the derivative of what's up in the exponent. So for instance, if we have the derivative, or we want to find the derivative of e, the 2x squared plus 1, this is the situation we're talking about. It's not just e to the x, it's e raised to some other function. And what the chain rule says is, because the first part is take the derivative of the outside, we get e raised to the 2x squared plus 1 back. So we get the same function again. But then the derivative does do something, because it says look at the inside function and find its derivative. And that is the power rule problem. The added 1, that becomes 0. When we use the power rule on x squared, the 2 comes down, so we get 4x. All right, so this is just a little strange, but I wanted to say something explicitly about it. But in some sense, it's more of the chain rule, just when the outside function is e, it looks a little bit different. Okay. And before we get into some different topics, I want to do one kind of last big example. So let's find f prime of x for this function. F of x is going to be e to the sine of 1 minus x squared. So in this case, there is actually 4 layers of function. The outermost function is e to the x. Then inside that is sine. That's the outermost thing in the exponent. Then there's also that we're raising something squared to the second power. And then also what we're squaring isn't even just x, it's 1 minus x. So we're going to have to repeatedly use the chain rule, working our way in until when we get to the derivative of 1 minus x at some point. That's a power rule problem. And that's where we'll be able to stop. So this is a case where I strongly recommend writing it out in a few steps. So the first step is, this is the type of function that we laid out here. The outermost function is e, so the first part of the chain rule doesn't do anything. So we get the whole function back again, e raised to the sine of 1 minus x squared. And this will be coming up shortly, but we want to make sure that this square is inside the sine function. So 1 minus x is being squared, and that whole thing is inside sine. It's not sine squared, which has come up in a few problems. So the first part of the chain rule here doesn't do anything, but we do have to take the derivative of the inside function. So when we move on, we have this part that we're done with. We're done differentiating, but we still have to carry it around. And now we have to take this derivative. And now there's a new chain rule here. The outside is sine now. The inside is 1 minus x squared. So sine becomes cosine. The inside stays what it is. And then we take the derivative of 1 minus x all squared. And focusing on this derivative, one thing which you need to make sure you don't purposefully do, but also make sure you don't sort of accidentally do this. 1 minus x is in parentheses. That whole thing is being squared. So you can't square the individual pieces or just x or something like that. We need to keep track of the fact that this is inside is 1 minus x, outside is the square. But when we get to this derivative, this is the chain rule problem, and it's the last thing that we'll have to do. So we still have e to the sine of 1 minus x all squared, and then cosine of 1 minus x all squared. When we take this derivative, the first part is a power rule. The 2 comes down, the inside 1 minus x stays there, and that's raised to the first power, which you don't have to write, but that is kind of literally what the power rule says to do. And then we have to take the derivative of the inside. It's not just x in there. And whenever it's not just x, you have to do some kind of chain rule problem. In this case, 1, that becomes 0, minus x gives us an extra factor of minus 1. And you could simplify this, but it's the only real thing might be multiplying these out a little bit, but that doesn't make it a lot better. Questions about this problem, which is big, but is not anything super new. The first step is this e to the x, which is a little bit different, but beyond that, it's some applications of the chain rule, which are similar to what we've seen. Okay. So that I just wanted to do, wanted to do just to make sure we had kind of one last pass at the chain rule. What I actually want to do next is use the chain rule to get a new derivative rule. So one thing that we don't have is what's the derivative of something like 2 to the x or 10 to the x. We only know the derivative of e to the x, which is just e to the x again. but we don't have the other exponential functions. And rather than just tell you this is what they are, what I want to do is actually see where the derivative rule comes from. And it's based on the chain rule in this version of the chain rule. So one fact, which is really just a super small version of the chain rule with e to the x, is if you're taking the derivative of e to the kx, where k here is some number, e to the 2x, e to the 5x, things like that, what happens is you get the same function again, but you multiply by the derivative of the inside. And if your inside is a number times x, the derivative of the inside is just that number k. And so the derivative of k times x is k times e to the kx. So if the only thing is you have a number, you get that extra factor multiplied out front. A second fact is not a calculus fact, but rather using some properties of exponential functions. And so if we have a to the x, a can be any number, not necessarily just e. This is equal to e to the natural log of a times x. So what's happening here is that this a is equal to this natural log, e to the natural log of a. Almost always, the way that you've seen this kind of move is you've said, oh, e to the natural log of a, e and the natural log cancel each other out. They're inverse functions, so they undo each other, and we're left with just an a. But you can also reverse it, kind of like if you multiply and divide by the same thing, that doesn't change your quantity. Even though most of the time you cancel something that is multiplied and divided, or that you're multiplying and dividing by, but you can also introduce it. Why this is useful, sorry, we don't need bright red. Why this is useful is we can also rewrite this using an exponent rule for dealing with a power to a power. So a power to a power, you multiply the exponents together. And so instead of e raised to the natural log of a raised to the x, we can multiply those exponents to get natural log of a times x. And the reason for pointing this out is a to the x, these are things we don't really know the derivatives of, but that is equal to an expression that looks like e raised to something. And this is a quantity that we can find the derivative of using what we know so far. So if we want to find the derivative of a to the x, so using the second fact, we can say, well, let's rewrite a to the x in this form, e to the natural log of a times x, because those are the same function. But then fact one says what you're doing is taking the derivative of exactly something of this form. The natural log of a is some number. It's not a nice number, but it is just a number. So using the chain rule, we get that there's an extra factor of the natural log of a, but then e raised to the natural log of a times x is still there. And the last thing we can do is say this e to the natural log of a of x, that was helpful for differentiating, but it's more complicated than it needs to be. Let's use fact 2 in the opposite direction, from right to left, to write this as an a to the x again. So the takeaway, the kind of main takeaway, is that the derivative of exponential functions, we now know what those are, even if it's not a to the x. For any other function, for any exponential function, you get the exponential function back with an extra factor of a natural log of a. What's also good to notice is that this fits with what we know. So if we use that rule to find the derivative of e to the x, well, this says, oh, it's an exponential function. That is the natural log of the base times the exponential function. But e is the number, so when you take the natural log, you get 1. So this is just e to the x. So the way that we could have approached this is, I could have told you this general rule for exponential functions at the beginning, and then said, as a special case, e to the x turns out to be its own derivative. Here we've taken kind of a different tack and said, we'll introduce e to the x on its own and combine that with the chain rule to get this more general derivative rule. Questions about, I guess, arriving at this new derivative rule? All right. So what we'll do next is because the situation is we now just have this derivative rule. We can sort of forget about where it comes from. And now this is another derivative rule, which we can use when we need to in some kind of problem involving derivatives. So let me see one of those. So let me clear this. So for instance, not be light blue. We could say, look at this problem. Let's find all x, where this function, f of x equals x times 2x, has a horizontal tangent line. So very much the kind of problem we've been dealing with, horizontal tangent lines, that's where the derivative is 0. But the new thing is, when we take this derivative, well, the first thing you'll want to recognize is this is a product rule problem. It's x times 2 to the x. So we'll have to deal with that. And then within the product rule, we have to take the derivative of each of the two pieces, and 2 to the x, that's an exponential function that our new derivative rule will apply to. So we'll start by finding the derivative, and I'll, at least this first time through, I'll kind of show the details. So the product rule says this is the derivative of the first part times the second function, and then flip that. Leave the x alone, and then find the derivative of 2 to the x. So the first derivative is easy. The derivative of x is just 1, so we just get 2 to the x. Over here, the derivative of 2 to the x, that's an exponential function that isn't e to the x. So that means we get an extra factor of the natural log of 2 times 2 to the x. And it's important to remember that this is not a power rule problem. The power rule says you have a variable raised to a fixed number, and that's where the power rule applies. Here, things are flipped. There's a fixed number down here, and the variable is in the exponent. So you don't want to bring down the x and have x minus 1. That's not the derivative. They have their own derivative rule, which says you get the function again, but with an extra factor. So that's where this natural log of 2 comes from, not kind of power rule type problem, but it's just a factor which appears in the derivative. So then what we can do next before we sort of move into the next part of this is, since we're going to be using this derivative for something, we'd like it to be factored. And the big factorization we can do is that both terms have a 2 to the x. In the first term, that's all there is. So we have a placeholder 1. In the second term, we have the x times the natural log of 2. Okay. So before we move into the back half, questions about getting to this point? Okay. So once we're here, we have our derivative. Now we want to set our derivative equal to 0. And since it's nice and factored, that means we have 2 equations, 2 to the x equals 0, and 1 plus the natural log of 2 times x equals 0. This first equation doesn't actually give us any solutions. And maybe the easiest way to see that is 2 to the x, its graph looks like e to the x. The values are different, but the same kind of large scale behavior is the same. It goes to infinity to the right and 0 to the left. And this never touches the x-axis. It has this asymptote where it gets close, but it never makes it there. So there's nothing you can put into 2 to the x to give you 0. And the other part, this is, despite the natural log of 2, a very simple equation. This is a linear equation that you've been solving forever. Just the natural log of 2 is a number that you sort of carry around. So you can subtract 1 from both sides. Natural log of 2 times x is -1. And then we can divide by the natural log of 2. Exactly what number it is, you'd have to check a calculator for, but it's not 0, so we can divide by it. And if you want, this number is approximately -1.44 if it helps to know what number it is, but that's not really necessary. This is exactly the number where this graph has a horizontal tangent line, and so that's the answer that we'll really be looking for. Questions about this problem? Okay. So in a lot of ways, this is like the problems we've been spending quite a bit of time doing, but we have a new derivative rule that gets included in the mix. So what I want to do next is, it seems a little scattershot, but I want to look at 2 different types of problems which on their own are kind of isolated, but they get us thinking about some ideas which are helpful for the next sort of big topic. So the first example of a problem which gets us thinking kind of in the right direction is that given this equation, x minus 1 equals f of x plus x squared. Let's find f prime of x. And there are really two ways to do this. One is solve this for f of x, then differentiate. So solving for f of x, that means we can subtract x squared from both sides. And that gives us x minus 1 minus x squared. And now once it's put in the sort of more standard form, the way that we've been looking at functions up until this point, now it's a sort of standard derivative. If we take this derivative here, the x becomes 1, the minus 1 becomes 0, and the x squared becomes 2x. So we can find its derivative. The second way is a little bit different, but will get us to the same place. What we'll do is we'll differentiate both sides of the equation, and then what we have, we'll have an f prime in it, and then solve for that. So what this looks like is starting from our equation, x minus 1 is f of x plus x squared. Take the derivative of both sides. And the way we're thinking of this is we're saying that this equation is saying here are two functions, they are equal. And if two functions are the same, then their derivatives are also the same. Once we're here, so we're doing the same thing to both sides of the equation, and what we get is still equal. For most of it, it's a standard type of problem. X minus 1, what's that derivative? Well, the minus 1 goes away, and we just get a 1 from the x. On the right, it's a little bit different, because when we take this derivative, we're saying, what's the derivative of f? Well, we don't know. That's what we're trying to find out. But what we can say is the derivative of f, whatever that is, I write that as f prime of x. And then x squared, that's something where we actually have the formula in hand, and that becomes 2x. And now we have an equation with f prime, and that's what we're really interested in. So now solve for f prime, which says subtract 2x from both sides. And we get 1 minus 2x, which is the answer we got before. Okay. Questions about this problem? So the calculus is not, the derivatives we're taking aren't overly complicated, but this second way is a way we haven't really thought about doing this. But it's a tool that we could use. Okay. So now I want to switch gears pretty completely to look at a different situation, but is also good to look at. Okay. So something that you've seen at some point, sorry. So something you've seen at some point is the volume of a right circular cylinder. So this is just the kind of standard can of soup cylinder, or sort of 3D rendering. So the right means that it's right angles here. Circular says the bottom is a circle, and cylinder says you go up with that shape. So the volume of this, the dimensions that we care about, the circle, which is kind of every cross section, especially the bottom and the top, that has some radius of r. And then this has a height h. And in terms of these dimensions, the volume is pi r squared h. Pi r squared, that's the area of the bottom, and h is the height. So it's like you're taking the area and you're stretching it out over height h. So this is the volume. There's, maybe you remember it, maybe you don't, but at some point when you've had a math class about geometry and shapes, this formula has appeared. So something that we can say, which ties this to calculus a little more, is if you increase the radius or height, either way, that increases the volume. But the question is, how fast? So if you have a circle or you have this cylinder, two ways to change it are make it taller, increasing h, or make it wider by increasing the radius of the circle that forms the base. And so those are both ways of increasing the volume, but it's not clear exactly how. So how do we, in changing these different dimensions, how do they affect the volume, and do they affect it in different ways? So the way that we can understand this is there are really two derivatives we could ask about. There is dv dr and dv dh. These are both rates of change of the volume, but this first one says if you treat r, the radius, as the variable, so you're increasing r while leaving the height fixed, how fast is your volume increasing per unit of the radius increasing? And dv/dh is kind of the opposite. This is saying if you leave the r fixed, so you're not making it any wider, but you're changing h, so you're making it upside down. So you're making it taller. How fast does the volume change if you're only making it taller? So these are two different derivatives, both derivatives of the volume, but we're looking at different variables in each case. And so if we want to compute them, the way that we do them in different ways. Here what we're saying is we're treating r as the variable, and that's what this expression is really saying. R is the thing that's changing. You're finding the derivative with respect to that change. And in this formula, the way that we look at it is, or to write it suggestively, is we'll write the volume as pi times h times r squared. Because if r is the variable, h we're leaving fixed, and since that doesn't have any r's in it, we're treated like a constant. So when we take this derivative, pi times h, that's a constant, and constants just come along when you differentiate. r squared, that's where the r is, and that's where we use the power rule. And you can rearrange things if you want, but the main point is when you're taking the derivative with respect to r, that's where you take the derivative, not in h. But you could ask, well, what is the derivative of the volume with respect to h? As you increase the height, how quickly does that increase the volume? And so here we're taking the derivative with respect to the variable h. So the way we'll want to think about it is there's this constant pi r squared, which doesn't have any h's, so that's fixed, but we do have this one factor of h. And so in this case, the way we look at it is h is the variable. It's not raised to a power. So when we take the derivative, what happens is we just get the number multiplied in front of h. Sorry, my h got kind of, okay. Should stop trying to fix things, because when I try to fix things, it just makes it look worse. So pi r squared. Okay, so these are the kind of formulas for telling you how fast things are increasing. Questions about this, either the calculus kind of process steps here, or what these derivatives are and how to go about thinking about them. Okay. So if there are any questions, then, so this type of problem, kind of dealing with different variables and how derivatives work with these different, as you choose a different letter, that and the previous problem, which is really differentiating both sides, while they're not of super interest on their own, that kind of thinking will be something we'll want to keep in mind for this next topic that we can at least introduce today. So here's a question which looks like something, or it makes sense, and we can kind of tell that it should have an answer, but we don't immediately have a way of finding the answer. So here's a question. What is the equation of the tangent line to x squared plus y squared equals 25 at the point 4, -3? So this equation here, as a reminder, is the equation of a circle centered at 0 with radius 5. So the picture of what we're actually looking for, there's, all right, that's not too bad of a circle. We have our circle of radius 5, the point 4, -3, so 4, -3 puts us somewhere around here. And for this point on the circle, you can draw the tangent line. So we can picture this situation fairly easily. We have a circle of radius 5, you pick a point, you can make a tangent line for it. And that line has to have some equation. But how do we actually do it? The problem that shows up here, or I guess not problem like homework problem, but the issue which makes it difficult, is that the equation doesn't define y as a function of x. So to this point, everything we've been doing has been f of x equals stuff with x. And in that case, you pick an x, there's one y that comes out. On this circle, you can pick an x, and there are two y's that correspond to it. So it's not a function. We don't have the circle isn't a function, but what we can say is that it implicitly defines y as a function of x. What that means is that if you only looked at part of the graph, for instance, if you just looked at, say, the top part of the graph here, the top part of our circle, that part is a function. And so while as a whole, it doesn't, you can't rewrite this so it looks like a function, but being implicitly defined as a function means that our calculus can still work on it. And relating this to the first sort of out of the blue type of problem where we had an equation is, I don't want red. So one thing we could do, we could solve this for y. If you solve this for y, that means you subtract x squared and take a square root. The problem is that you get a plus and minus. You're taking the square root of a square. And so the plus minus is really saying each x gives you two possible y's. But what actually happens is the positive square root is the top. If you graph this, that gives you exactly the upper semicircle. And the negative square root is the bottom. So one way that you could do this problem is this negative square root function gives you the bottom, and then do our standard calculus on this function with x equals 4. But the problem is that what if we weren't so lucky? What if you can't solve for y? Then we can still answer this type of question, but we have to use what's called implicit differentiation, which is a way of dealing with questions like this. You're given an equation with which, if you graphed it, tangent lines would make sense and it would implicitly define a function, but maybe you can't solve for it. So we need to talk about how can we answer this type of question without solving for y and just dealing with the equation as we're given. And so that's what we'll pick up with next time. And how it works is using the chain rule is kind of a key ingredient. So if anyone has any questions, I can stick around for a little bit, but if not, then I will see you guys on Friday, as long as everything goes well today, getting my car taken care of. Questions before I head out? All right. See you guys later.